What specific problem does your proposed method aim to solve in relation to the extreme token phenomena observed in transformer-based LLMs? Can you elaborate on the consequences of these phenomena in downstream tasks?
The proposed method aims to address the extreme token phenomena in transformer-based large language models, LLMs, specifically the issues arising from sync tokens that receive disproportionate attention, leading to reduced interpretability and performance in downstream tasks. These phenomena complicate long context inference and model quantization, as sync tokens require special treatment to maintain performance levels. The extreme token phenomena also result in attention sinks and value state drains, where non-extreme tokens contribute minimally to the residual stream, further degrading model performance. By introducing architectural modifications, such as replacing softmax with ReLU activations, the method seeks to eliminate these extreme token behaviors, thereby enhancing the model's ability to generalize and interpret attention maps effectively. Ultimately, the goal is to improve the overall performance and reliability of LLMs in various applications by mitigating the adverse effects of these phenomena.
How does the proposed method work? Illustrate the key algorithmic steps involved in addressing the identified issues related to extreme token phenomena, particularly the structures and functions of the active-dormant and mutual reinforcement mechanisms.
The proposed method addresses the extreme token phenomena by introducing the active-dormant and mutual reinforcement mechanisms within transformer architectures. The active-dormant mechanism classifies attention heads as either active, contributing significantly to the residual state, or dormant, contributing minimally, depending on the token being processed. This classification allows the model to focus attention on trigger tokens, while minimizing attention on non-trigger tokens, effectively creating attention sinks. The mutual reinforcement mechanism posits that when an attention head can predict the next token without its contribution, it becomes dormant, reinforcing the attention sink at special tokens like the beginning of sequence token. Key algorithmic steps include training transformers on tasks like the bigram backcopy task to observe these dynamics, and modifying the architecture by replacing softmax with ReLU activations to disrupt the mutual reinforcement, thereby preventing the formation of attention sinks and value state drains.
Can you provide a simple yet illustrative example that demonstrates the inner workings of your proposed algorithm, particularly through the bigram backcopy task? Walk through the main algorithm steps with this example.
To illustrate the inner workings of the proposed algorithm through the bigram backcopy (BB) task, consider a sequence starting with the beginning of sequence token, text S. In this task, the model generates tokens based on a predetermined bigram transition probability, P, and when it encounters specific trigger tokens, it copies the preceding token instead of sampling from P. For example, if the sequence begins with text S followed by summer, and the next token is a trigger token is, the model will copy summer to the next position, resulting in the sequence, text S, summer is summer. The algorithm operates in two main phases. During the active phase, the attention head focuses on the trigger tokens, contributing significantly to the residual state, while in the dormant phase, it becomes less active for non-trigger tokens, leading to attention sinks. As the model trains, the attention weights on the text S token increase, indicating it is becoming an extreme token, while the value state norms decrease, demonstrating the value state drain phenomenon. This dynamic interplay between the active-dormant mechanism and the mutual reinforcement mechanism drives the model's learning process, allowing it to effectively handle the BB task.
What are the key theoretical and practical benefits of your proposed method when compared to existing approaches for mitigating attention sinks and value state drains in transformers?
The key theoretical benefit of our proposed method lies in its foundation on the mutual reinforcement mechanism, which explains the formation of attention sinks and value state drains in transformers. By replacing softmax with ReLU activations in attention heads, we disrupt this mutual reinforcement, preventing the dynamics that lead to extreme token phenomena. Practically, this modification has been shown to eliminate attention sinks and value state drains in the bigram backcopy task, allowing for more stable training dynamics without the adverse effects observed in existing methods that rely on softmax. Additionally, switching from the Atom optimization algorithm to SGD further mitigates residual state peaks, enhancing model performance. Overall, our approach offers a more robust framework for addressing these issues, as evidenced by the consistent improvements in training outcomes across various transformer architectures.
How did you validate or test the effectiveness of your proposed method? Please detail the experimental design, datasets, and metrics used to evaluate performance.
To validate the effectiveness of our proposed method, we conducted experiments using a simplified transformer architecture, trained on the bigram backcopy (BB) task, which exhibits extreme token phenomena. We trained 1 to 3 layer transformers on this task, utilizing a dataset derived from the Tiny Shakespeare dataset to establish a bigram transition probability. The performance was evaluated by measuring the attention weights, value state norms, and residual state norms, particularly focusing on the behavior of the sync token, text S. We specifically observed the dynamics of attention sinks and value state drains, confirming the mutual reinforcement mechanism through quantitative predictions that aligned with our theoretical framework. Additionally, we tested modifications such as replacing softmax with ReLU activations and switching from Atom to SGD, which demonstrated significant changes in the dynamics of attention and residual states, further validating our hypotheses regarding the extreme token phenomena.
What specific results did you achieve with your new method, particularly in terms of improvements over previous models? Can you quantify these results in relation to performance metrics?
In our study, we demonstrated that replacing the softmax activation function with ReLU in attention heads effectively eliminates the extreme token phenomena observed in the bigram backcopy (BB) task. This modification led to both the bigram and backcopy risks converging to the Bayes risk after just 200 training steps, indicating a significant improvement in model performance. Additionally, we found that switching from the Atom optimization algorithm to SGD removed the residual state peak phenomenon, further enhancing the model's stability and interpretability. Our empirical results showed that the attention logits for the sync token did not increase, and the value state norms remained stable, contrasting with the behavior of previous models that exhibited attention sinks and value state drains. These findings quantitatively highlight the effectiveness of our proposed architectural and optimization changes in mitigating the extreme token phenomena in pre-trained LLMs.